Good afternoon, everybody. Thank you again for coming to the Jackson School DeFord Lecture Series from the Department of Geological Sciences. The DeFord Lecture Series has been a tradition within the Geology Department since the late 1940s. It's been a long-standing venue for disseminating research from both our own graduate students, faculty, researchers, and distinguished researchers from the outside community. It is named after Ronald Kinnison DeFord, who joined the university as a professor back in 1948. He served as graduate advisor for the department from 1949 to 1967, and he supervised an amazing 19 PhD students and 126 master's theses. Many of those theses were based on fieldwork done right here in Texas, out in West Texas and in northern Mexico. One of his enduring contributions to the department was his leadership in organizing and running what at the time was called Technical Sessions, our speaker program. And so in honor of his contributions, we renamed Technical Sessions the DeFord Lecture Series a couple of years ago. And as I said, this is a venue where we can bring in distinguished researchers from around the world to present their research to the Jackson School. Today, I'm very happy to welcome Dr. Xiaowei Chen from the University of Oklahoma. Fortunately, sound is off, so we don't have all these boos coming about Oklahoma because they apparently have a better football team than we have. With that said, however, I'm going to hand over to Peter Flemons. Will tell us a little bit more about Dr. Chen and what she's going to be talking to us about today. So thank you very much.
I'm really pleased to introduce Xiaowei Chen. Professor Chen is an associate professor at the ConocoPhillips School of Geology and Geophysics at the University of Oklahoma. Prior to Oklahoma, she was a postdoctoral researcher at Woods Hole and a visiting postdoctoral fellow at the Earthquake Research Institute at the University of Tokyo. She received her PhD in 2013 at the University of California, San Diego. She also received her MS at Scripps and her undergraduate degree at the University of Science and Technology in China. Dr. Chen has made fundamental transdisciplinary contribution towards understanding the processes driving induced seismicity through the coupling of seismic studies with poroelastic flow models. Much of her talk today is centered on the problem of wastewater injection wells, but the problem that she is focusing on spans wastewater injection. It extends into geothermal energy, CO2 sequestration, and to understanding natural earthquakes. And she's worked in most, if not all, of those problems. The other thing I'd like to say is that for students, Dr. Chen has a vibrant research program. You can see on her website that she's looking for graduate students on a range of problems, and it looks like a pretty exciting team. And so with that, Xiaowei, I will hand it off to you, and thank you very much for coming to Texas digitally, even though we don't like your football team.
Okay, all right, thank you. Is everybody able to see my screen? Okay. Yes. Okay. All right.
Sorry. Yes, that looks great.
Okay. Thank you, Peter, for the invitation and the introduction. So our department actually went through a name change. We are currently officially School of Geosciences. So I want to acknowledge support from our department and funding from USGS, OGS, and ESF. And this talk combines several different studies and involves collaborations from many different people. And I will be introducing each individual studies in a second. So this is my brief outline. I will start with the treating and followed by observations of the seismicity and the modeling of power pressure and the poroelastic stress and observations of the stress state of different faults. And then I will go into details for individual sequences and discuss the diverse triggering process for individual sequences, followed by overview of triggering process in Oklahoma. So this is a general talk, so I want to briefly introduce the concept of earthquake triggering. The first slide is showing a block sliding model where the weight of the block is kind of the normal stress, and the friction resistance is the product of friction coefficient and normal stress in this case. And somebody is pulling the spring and simulating the shear stress, and the spring is stretching and simulating the stress loading process. So when the stress is overcoming the friction, they will have a seismic slip, and followed by relaxation of the spring and relaxation of the stress. And there begins another cycle of stress loading and seismic slip. And what is earthquake triggering? Earthquake triggering is there are some external forcing that contributed to generating the movement of the block, which in our case is the occurrence of the seismic slip. So this is kind of the triggering could accelerate the earthquake occurrence ahead of this normal earthquake cycle. Now we're going to a little bit more quantitative and looking at the Coulomb failure envelope. And this is a small sample here. And there's a maximum principal stress and minimum principal stress. And there's a fracture at angle theta relative to the maximum principal stress. And we can plot this on the Morse circle, and the y-axis is the shear stress, and x-axis is the normal stress. And then when the Morse circle intersects with the Coulomb failure envelope, we can generating a force slip. And the Coulomb stress is the difference between the shear stress and the friction coefficient multiplied the effective normal stress, which is the difference between the normal stress and the pore pressure. We can look at earthquake triggering in the Morse circle and the Coulomb failure sense. So if the original stress state is far from the Coulomb failure envelope, there are two ways we can generating the failure. We can modify the principal stress field. And in this case, we kind of enlarges the Morse circle and generating a seismic slip. Or we could increase the pore pressure. As we increase the pore pressure, the whole Morse circle is shifted to the left. And this, we can also generate a seismic slip. So in a summary, there are many processes that can trigger earthquakes. For example, we have dynamic triggering, groundwater recharge, and tidal forcing, and volcano activity. So these are natural triggering process. And we have man-made process like reservoir impoundment, fluid injection, geothermal, thermal contraction, and hydraulic fracturing. Right. So there are common procedures that lead to induced seismicity in the mid-continent of the US, has a small percentage coming from hydraulic fracturing. For example, in Ohio, there are several cases of hydraulic fracturing induced seismicity. And hydraulic fracturing is trying to inject into the production formation, trying to generating a fracture network that can enhance the permeability. And there's a small percentage coming from enhanced oil recovery. And this is kind of water flooding, trying to sweeping the resources towards the production well. And there's a large percentage is coming from wastewater disposal, where the wastewater is kind of a byproduct from the oil productions. For example, in Oklahoma, for 1 barrel of oil, we have about 7 to 9 barrels of wastewater. And those wastewaters are injected into a deeper formation that can trigger some earthquakes. There are 4 magnitude larger than 5 earthquakes happened in Oklahoma in the past 10 years. And the PAWNEE earthquake 2016, Cushing earthquake 2016, magnitude 5, and the Prague earthquake 2011, magnitude 5.7. And all these 3 earthquakes generated some structural damages to local structures. And the Fairview earthquake did not cause as much damage because it's relatively remote in the location. And this is an example of observations following the PAWNEE earthquake. As you can see, there are lots of fractures caused by the earthquake, and there's smaller scale fractures and also sand blows. Sand blows is kind of a form of liquefaction of the soil, and all these are caused by this magnitude 5.8 PAWNEE earthquake here. So now I'm going to look at the seismicity and relationship with pore pressure diffusion. Before I start, I want to briefly introduce the tectonic background. So Oklahoma is part of the Southern Granite Rhyolitic Province. And you can notice that the northwestern part of Texas is actually in the same granite rhyolitic group as Oklahoma. So there would be a lot of similarities between Oklahoma and Texas induced seismicity. And the Southern Oklahoma allocation is a failed rifting arm happening in about Cambrian age. And in Oklahoma, we have two major fault systems. One is the north-south oriented Nemaha Fault. And you will hear the name Nemaha Fault several times throughout this talk. And there's the Mills Fault. The Mills Fault is located in southern Oklahoma and hosted about magnitude 7 earthquake around every 1100 years. So if you look at the USGS earthquake hazard map for Oklahoma, most of the seismic hazard would be dominated by the Mills Fault in the pre-2009 earthquake hazard map here. And the seismicity mostly happened in the Anadarko Shelf and the Cherokee Platform. And you can notice that so the left figure is showing the earthquake and station distributions, and the right-hand side is showing the disposal well distributions. So you can notice that the seismicity are mainly associated with the disposal wells in these two regions. In the Anadarko Basin, we have a lot of hydraulic fracture-induced seismicity, mostly associated with the scoop and stack plate. And in the Acoma Basin, we also have some hydraulic fracture-induced seismicity. So the first thing I want to show is kind of the movie showing the spatial temporal correlations between seismicity and the earthquakes. So downward triangles are disposal wells. That the size of the disposal well is corresponding to the injection rate, and the earthquake size is corresponding to the magnitude, and their depth is corresponding to this color bar here. As you can see that originally, so this is the Prague sequence happened in 2011. Originally, most of the earthquakes are in the central eastern Oklahoma, and the northwestern Oklahoma doesn't have any earthquakes during this time period, but there are some disposal wells here. And throughout into 2013, we started to have some earthquakes around this region. And then we started to have new disposal wells and new seismicity around those disposal wells. And in 2014 and 2015, it's getting a little bit too crazy. So it's really hard to track individual sequences anymore. So eventually, if we look at the overall state, we have strong correlations between the injection rate and the seismicity rate. So the time delay is around 200 days, about 2 years, 1 or 2 years time delay between the peak injection rate and the peak seismicity rate. So spatial temporal correlation and spatial temporal association is when usually most induced seismicity research begin. The common mechanism for injection-induced seismicity is increased pore pressure. So this is showing the left figure is showing the pore pressure distributions in space and time from a single injection source with a constant injection rate. And the right-hand side is showing the seismicity rate generated from the pore pressure distributions. So you can see that the seismicity gradually expands in space and time, follows the pore pressure diffusion, right? So now we are going to, well, this is a theoretical modeling and has been very similar to the observations of microseismicity from hydraulic fracturing. And you can see that the diffusion curve kind of captures the spatial expansions of the seismicity really well. So now we are going to apply this to Oklahoma. Oklahoma is a little bit complicated because we don't have a single injection source. We have many disposal wells, but we have this kind of concentrated injection in these high rate injection regions in those white line and the red line. Red line is 95 percentile and white line is 99 percentile. So my student Jackson kind of has an idea that we use a proxy of the center of the high rate injection regions as a seed points for the injection source. And then we can use this to look at the regional scale migrations of the seismicity. We divide this into 7 different regions. And then for each region, we look at the spatial distributions of the seismicity from this injection source, kind of hypothetical seed point here. The result is showing that we have very good large-scale diffusive migrations. This is region A located in northwest Oklahoma, and the distance ranges from 0 to 45 kilometers. And this region J in central eastern Oklahoma, and this is showing a very good diffusion extending up to about 50 kilometers. And the Nemaha fault here serves as a fluid pressure boundary and separating this into north central Oklahoma, northwestern Oklahoma, and central Oklahoma here. And these 2 regions have different diffusivities. And for west, it has a really high diffusivity around 2.25, but in central Oklahoma, it has a relatively lower large-scale diffusivity. Right? So these are the large-scale patterns. Now we are looking at a local scale within individual fault. And this is a fault located in central Oklahoma. We term this as a Guthrie sequence because it's closer to the city of Guthrie. And you can notice that this sequence itself also shows a very good diffusive migrations in the fault zone. And the diffusivity is around 0.04 meters squared per second. So this is much lower compared to the large-scale diffusive migration, right? So we can apply this to many different sequences in Oklahoma. We identified up to about 20 to 30 individual seismicity clusters, and we find about 6% of the clusters showing statistically significant migrations. And this figure is showing a stacked image from all the sequences, and you can see that they are kind of very well explained by a diffusive migration, okay? And the diffusivity value is around 0.05 meters squared per second, and this represents the hydraulic properties of the crystalline basement, and they are much smaller than the regional scale diffusivity, which is ranging from 1 to 4 meters squared per second, representing the abaco formation, which is the injection layer, all right? So with this, we can derive a 2-layer diffusivity model based on this kind of multi-scale analysis of the seismicity. We have the long-range pressure propagation is facilitated by the high diffusivity within the abaco layer. And we have the faults in the crystalline basement have relatively lower diffusivity and similar to kind of tectonically active regions such as California. So now this part covers the relationship between pore pressure diffusion and seismicity, but is pore pressure the only story? Well, this figure is from Sigon and Liu 2015, and in addition to pore pressure, the elastic stress field also changes due to the volumetric strain changes. So we might want to look at coupled response between rock deformation and pore pressure. So rock deformation can influence pore pressure changes, and pore pressure can influence rock deformation, right? So now we are going to look at the modeling part, including pore pressure and pore elastic stress, and mainly coming from these 2 studies from Guangjai and Thomas Goebel. This figure is showing the coupled pore elastic response change seismicity rate responses. So the left figure is showing the coupled response from pore pressure and pore elastic responses, and this is the associated seismicity rate. And the right-hand side is showing the difference between the seismicity rate from pore pressure only and the coupled response. So we can notice that the uncoupled model that we only consider pore pressure can overestimate rate at closer distance, but underestimate at further distance. So we apply this to Oklahoma, and we try to divide Oklahoma into 2 major regions separated by the Nemaha fault, because this is 2 different pressure regions, and the Nemaha fault kind of serves as a pressure barrier. Western Oklahoma and central Oklahoma. And this is the data. So monthly injection rate for Central Oklahoma and seismicity observations from Central Oklahoma. And this is West Oklahoma. In both regions, we have very strong temporal correlations between the seismicity rate and injection rate. So this model result is presented here. So the red blue line is showing the Coulomb stressing rate changes. The dashed line is showing the pore pressure only, and the solid line is showing the coupled response from both pore pressure and pore elastic response. So what you can see here is that the pore pressure amplitude is much larger than the pore elastic stress amplitude, and it kind of dominates the stress change. And the top figure, the red line is showing the seismicity rate predicted from the stressing rate changes. So the dashed line is again predictions from pore pressure only, and the solid lines is predictions from both pore pressure and pore elastic stress. So what you can see here is that although the pore elastic stress amplitude is relatively small, it amplifies the seismicity rate significantly by 3 or 6 times compared with using only pore pressure for both Central Oklahoma and Western Oklahoma, right? So which one matches the observations better? Okay, so now we can compare the predictions with observations. So the left column is observed seismicity rate. These are individual magnitude versus time, and the histogram of the seismicity rate and the probability density function of earthquake versus time. And the middle panel is simulation using only pore pressure, and the right is simulation using both pore pressure and pore elastic stress. As you can see that the right column matches the observations much better compared to observations using only pore pressure. So this is showing that the pore pressure and pore elastic stress both need to be considered in the modeling part. And this need to new value of induced seismicity to include the pore elastic stress. In the classic value, for example, in the geothermal stimulations, the seismicity only occurs in region affected by the pressure change. But in the present value, the stress change can propagate to a much further distance and through the coupled pore elastic responses. So a side note is that the stress change will depend on the background stress field and fault orientations, right? So our next question is, what are the stress field and fault stress states in Oklahoma? So this is the third part about the stress and the faults. Oklahoma faults ready for failure. The major credit is Yan-Qin, and she is this person here, and she participated in the PAWNEE earthquake rapid response deployment. And you can notice this is a solar panel, and this is a recording boxes, and the box is connected to the sensor, which is buried in the background. And you can notice that we put a fence for the stations. And in most Oklahoma field, we have a lot of cattle. And this is a cattle, about 40 cattle surrounding our field deployment. And cattle really like to chew on the solar panel. So that's why we need to protect them using the fence here. So I'm going back to the classic Coulomb failure envelope. And in this case, I want you to pay attention to the fault orientations. So in this case, for the fault oriented at this angle theta, and we plot the stress state for this fracture, and it's perfectly aligned with the Coulomb stress failure envelope. So we see these faults are optimally oriented in the given stress field. And then we look at another fault at a different orientation. So we plot the stress state here, and you can see that it's far from the failure envelope. So we see that faults of different orientations are not optimally oriented in the given stress field, right? In Oklahoma, we further quantify the optimal orientation using a parameter called understress for each fault. So understress near 0, which are closely located to a failure envelope, they are optimally oriented. And for understress of 1, mean they are not optimally oriented. right? So we started using the focal maximum solutions to do a stress field inversion, and we're mapping the fluid pressure focal maximum using a focal maximum tomography method, and then we calculated the under stress for each fault that we were able to map. And this is the result of the stress field. Again, this Nemaha fault appears here and separating different pressure units. So the background is the pore pressure calculated by Matt Weingarten, and the lines are showing the stress maximum principal stress orientation, and green is the stress sleeve faulting, and the black is oblique normal faulting. So we can notice that different faulting styles across the Nemaha fault. In northern Oklahoma, we have a combination of oblique and stress sleeve faulting, and in central is mostly stress sleeve faulting in the larger scale. And the dominant stress orientation is around 80 to 90 degrees throughout Oklahoma. And this figure is showing the seismogenic faults. And for each of the faults, we were able to calculate the excess pore pressure required for failure for each fault. So red, it means that the fault is optimally oriented and doesn't require a large pore pressure to trigger this fault. But blue means that it's not optimally oriented in this case. And then we can plot individual faults on the Morse circle. As a result, we find 78 faults are critically stressed with under stress lower than 0.2, and non-optimally oriented faults are being activated kind of primarily in some of the high pore pressure regions due to some other process like stress interactions from earthquakes. And then we want to look at these 4 large earthquakes. As you can see, these 3 earthquakes are mostly colored by red, meaning that they are optimally oriented. But for the Fairview earthquake, it's not as well oriented as the other 3 earthquakes. We will look at this in a little bit detail. So this is showing a comparison of seismogenic fault and sedimentary fault. And the red is showing northwestern Oklahoma, and blue is showing central eastern Oklahoma. And this yellow are showing exposed fractures in the South Oklahoma. So we can notice that the seismogenic faults and the sedimentary faults in western Oklahoma are kind of very well correlated, but in the seismogenic faults and the sedimentary faults in central Oklahoma, they have very different orientations, right? So most of the seismogenic faults are not previously mapped in Oklahoma. And most of the mapped faults primarily occurs in the sedimentary layer in most cases. So the faults with magnitude 5 earthquakes, as I mentioned that the Fairview earthquake is not very well optimally oriented. And we can notice they are different in the temporal evolutions. So for Prague, Pawnee, and Cushing, they kind of dominated by the large earthquake with very little seismicity beforehand. But for the Fairview, we can notice there's a gradual build-up of seismicity and a gradual increase of the magnitude before reaching the magnitude 5 earthquake. So this is indicating that the fault structure and the fault stress state could influence individual sequence evolutions, right? So next question is, what drives the spatial temporal evolution of individual sequences? Okay, so with this, we are going to look at individual sequences and trying to identify diverse triggering process involved in each sequence. Okay. So this is the same figure that I showed before. The background is pore pressure, and then the individual faults are color-coded by their excess pore pressure. So red are optimally oriented, and this blue and cyan are not as well oriented. So we are going to look at 3 individual faults. One is the Woodward, located in northwestern Oklahoma, and one is the Guthrie sequence, located in central Oklahoma, and one is the Pawnee earthquake, located in the northeastern Oklahoma. Right. So for the Woodward, we kind of sequential fault activation due to Coulomb stress interactions. And for Guthrie, we have earthquake interactions and potential aseismic slip. And for PAWNEE, we have Coulomb stress loading from fault shocks and possible aseismic slip. Okay, so we'll start with Woodward sequence. And Woodward sequence, this is showing a number of earthquakes versus time and magnitude versus time. From the temporal evolutions, we were able to divide the Woodward sequence into different stages. We have identified 6 different stages of the Woodward fault. Interestingly, each of the stage is rupturing a separate fault segment. And in stage 1, you can notice that the seismicity are mostly located in a step over. And in stage 2, it occurred along the main fault, but in a southwestern segment. And in stage 3, it ruptured the northeastern segment of the fault R1. So we divide the faults, we kind of simplify the modeling. We only use 3 different fault segments. R3 and R1 are stress slip, and R2 is kind of a normal faulting that is a step over here. So we look at the Coulomb stress interaction between different stages. All right. For each of the stage, we use the seismicity and calculate kind of the total combined seismic slip, and using the Coulomb stress software to model the Coulomb stress changes. This is the result for stage 1. So the seismic slip is occurring in the R1 fault, and then it causes the positive Coulomb stress changes in the southwest segment of the fault R1. And you can notice that the seismicity in stage 1 mostly occurs in the positive Coulomb stress change area. And in stage number 2, it caused the positive Coulomb stress change in the next stage. So seismicity occurred in stage 3, mostly occurred in some of the positive Coulomb stress change from stage 2. So we have kind of the sequential cascading failure activating different fault segments. And the Coulomb stress amplitude from the earthquakes has a similar amplitude to the power elastic stress from injections. So previously, Thomas Goebel did a power elastic stress modeling for Western Oklahoma, and we found the stress amplitude from the power elastic stress is around about 0.1 to 0.2 megapascal. So this indicating that for the induced earthquake sequences, the stress interactions from the earthquake themselves are as important as the stress introduced by the injection themselves. And then we are going to the Guthrie sequence. This Guthrie sequence, we have been working on this sequence kind of like forever. So the sequence first started by a discussion with Austin Holland, who was the previous Oklahoma Geological Survey state seismologist. And there was a report that this well might be causing the seismicity. So we started to analyze this sequence, and we included more wells nearby. So we considered the 3 major wells that are close by to this sequence, and we also included some distant wells. So the size of the well is actually corresponding to the injection volume. So you can notice that the well that people reported has actually very low injection volume here. The whole sequence is exhibited a very good diffusive migration, as I previously showed. And in this study, we also look at the background seismicity rate variations from statistical analysis of the seismicity. So in the statistical seismology, we can separate background seismicity rate that are due to external process, for example, slow slip or fluid signal, and separate them from the triggered aftershocks. So this blue curve is removed all the contributions from aftershocks and only showing the seismicity rate from the external triggering process. And those colored lines are showing the injection volume, and the red is showing the combined injection volume from all the 3 wells. and the purple and the green are showing the individual well injection rate variations. So you can notice that at the beginning, the purple well that are closer to the sequence started injection, followed by a rapid increase in the background seismicity rate variation. And this is corresponding consistent with a fluid-driven fault activations, possibly indicating there is a fluid conduit that linking this photo well to this seismogenic fault to leading to this rapid response. And then we identify two anomalous stages, and one is a stage where we have a decrease in the injection volume, but an increase in the background seismicity rate. And from the spatial migrations, we can see there seemed to be kind of a linear migration, and there were 3 large earthquakes. So these circles are showing earthquakes larger than magnitude 3. So we think this is a potential aseismic sleep period, and I will show a little bit more details later. And the other stage is showing the magnitude 4 earthquake that corresponding to low background seismicity rate and lower injection rate. So the 2 injection wells are kind of shut in towards the end of the sequence here. And this is the location of the magnitude 4 earthquakes. I'm going to show this in the next slide. So we identified the Guthrie sequence with different stages, and this is the overall distribution of the seismicity. So it's dominated by Straxley faulting in the southwest orientation, southeast orientation. And this orientation is kind of optimally oriented in the local stress field. Okay. And then we will focus on the potential slow sleep period. So we are focusing on seismicity occurred during this time period. And this figure is showing the time versus the distance along the east. So this is from west to east. And this is showing the focal maximum solutions. And the blue is showing the right lateral Straxley fault. And this green is showing a separate fault that is a kind of left lateral Straxley fault. And we identify that there is a spatial migration along this kind of normal faulting around 0.53 kilometer per day. And this is combined with some other evidence. We identify a slow sleep period that occurs on this normal faulting. So this normal fault is cutting through the main Straxley fault at a different orientation compared to the main fault. So this defines a very complicated fault mesh network in this small region. And then we look at the magnitude 4 earthquake time period. We identify a series of cascading failure. So first, we have 2 fault shocks that are triggering the first sub-event, and the first sub-event leading to the second, the third, and the fourth sub-event. And the fourth sub-event is triggering an early aftershock. So this is a series of cascading failure, just like faulting like a domino. So the rupture is involving diverse triggering process at different stages within the same sequence. Right. So for the Pawnee earthquake, this is kind of the largest instrumental recorded earthquake in Oklahoma. And we published a study in 2017 to look at the interaction between the fluid injection, the faulting, and the fault shocks, and the Pawnee shock itself. This defines I call this a Pawnee triple junction because it involves a intersection of a mapped fault and another mapped fault that is optimally oriented, and a previously unmapped fault where the main shock rupture occurred. And this is kind of the detailed view of the fault shock sequences occurring in the small region here. So for this fault shock, for this Pawnee earthquake, we identified kind of near simultaneous rupture along this previously mapped fault and a Pawnee, the main shock fault. So you can see that there are nearly simultaneous earthquakes occur on these 2 faults. Green is on the previously mapped fault, and red is along the main shock fault. And in the main shock fault, we also identified kind of a slow propagation, but this propagation is not as well resolved as the previous Guthrie sequence. And then collectively, we also analyze the Coulomb stress interactions between fault shock and the main shock itself. So all the red are showing the earthquakes that received positive Coulomb stress changes from previous earthquakes. And you can notice that most of the earthquakes were kind of received positive Coulomb stress changes from the 3 large fault shocks here, shown by the circle here. And the main shock itself received about 0.6 bars of positive Coulomb stress change from the fault shocks combined. So this is indicating that the PAWNEE main shock itself is triggered by diverse triggering process that involves fluid injection and the fault interactions and earthquake interactions. Right. So now I'm going to come to an overview of the Oklahoma induced seismicity. So this is a figure I previously made for a natural earthquake sequences. But in Oklahoma, we also identify a earthquake to earthquake triggering, and we also identify fluid triggering and also aseismic slip. So in this sense, Oklahoma earthquakes are kind of similar to natural earthquake sequences. And fluid induced seismicity in Oklahoma offers a window into naturally occurred earthquake sequences and kind of the general earthquake sequence evolution. And the role of earthquakes themselves and other types of fault slip are just as important as stress induced from fluid injection itself. So in this case, most of Oklahoma earthquakes don't have a dominant main shock, and we have this kind of gradual seismicity rate changes that involve both earthquake to earthquake triggering and those underlying external physical processes. So in an overview, we started with space and time patterns and associations, and we performed a regional scale analysis and to analyze the average behavior for the earthquakes and identified kind of large scale hydraulic models. And then we also analyzed the large scale stress distributions and fault distributions. And then we were able to dive into local scales at a much smaller scale, around 4 to 10 kilometers, depending on different faults that you're looking at. And the local scale, we can look at detailed stress and fault distributions, and we were able to identify complex interactions among multiple physical processes, and that drives the evolution of individual sequences. So this provides us with kind of the better understanding of the physical process that cause stress changes on seismogenic faults and the physical model that link stress changes with fault slip, right? And it kind of also offers us with better understanding of the general earthquake and the fault slip process with interactions of different physical process. For the future work, I think comparative studies of natural earthquakes and also comparative studies between Oklahoma and Texas would be very interesting, because the first figure kind of show Oklahoma and Texas are located in the same granite and rhyolitic rock group. And secondly, we could also incorporate the complex fault structures into modeling and trying to better understand the maximum magnitude and earthquake sequence evolutions, especially consider the role of aseismic slip in those modeling would be very beneficial. And then I want to show off a recent deployment that we did in North Oklahoma. And this is the city of Enid, and this is way northern Oklahoma, and there's a lot of wind farms. And this is me doing a field work and taking pictures in the field. This is good because we don't have as many cuttles along the state highways. And we installed a dust array at this location, and the dust array was recording about 97, 92 seismic channels in this area. And there's a local earthquake, 1.89, that are very close to the dust array. So we were able to identify the earthquake signal very clearly on the dust data. And we were also able to identify different vehicles traveling different directions at different speed. For example, this is a slow vehicle traveling along a residential road. So this is a residential road here. And those are the state highways. And those are offering some really exciting research that can potentially help us better image faults and earthquakes and perform smart city monitoring. So I have a student that's working on identifying traffic signals from the dust data. All right, I will stop here and take any questions. Thank you very much for listening.
All right, thank you very much, Xiaowei. Very interesting talk. Thank you again, everybody, for joining us this week. And please join us next week for another edition of the DeFord Lecture Series. And if people have additional questions, I don't know if Xiaowei has a couple minutes to stick around, but thank you again for a very interesting presentation.
Thank you, Xiaowei.
Thank you.